Hello everyone, welcome to the Gen AI training. Today we will be covering topics, what are transformers, some important abbreviations. We'll look into the deep neural network, training language model and vectorization. So let's start with the transformers. So what are transformers? So in layman language, if I explain the transformers, in normal day-to-day life, we see transformer. It is a big electrical equipment where we pass the input low voltage or high voltage and then transformer converts that high voltage into the low voltage as per your house appliances. So this conversion part that takes place inside this transformer that we will look into it. If we compare it with to the Gen AI, in the Gen AI also, we provide some input and we get the output. So how the transformer model it looks like. So in the similar way, we pass the input embedding. So what is the input embedding? The input token which we call it as a word or subwords are converted into dense vectors known as embeddings. This allows the model to handle textual data in a format that can be processed by the neural network. Tokens converted into then input embedding, it passed the input to further, and here we have the multi-head attention. Now the multi-head attention, it received the input from the input embedding, but in between there comes the positional encoding. Now positional encodings, these are the transformer that does not have a built-in mechanism for understanding the order of input tokens. Unlike RNNs, positional encoded is added to the input embeddings. So these positional encodings we adding to the input to the input embedding. This encoding injects information about the token's position in the sequence, helping the model understand the order of words. So it helps in understanding order of words. Now once it passed to the multi-head attention, now multi-head attention is a key part of the transformer architecture. It allows the model to focus on different parts of the input sequence at once. In multi-head attention, the input data is transformed into several different subspaces, and attention is applied in parallel multi-heads. The output from each head are concatenated and processed. So in the encoder, this attention mechanism allows each token to attend to all other tokens in the input sequence. So if we try to understand this, output from each head is concatenated and processed. Now multi-head attention, that is added with one more flavor, that is the add and norm, which passes the input to the add and norms. The output from the multi-head attention is added to the input via a residual connection, which we call it as a skip connection, and then the result is normalized. This helps the model to retain the original information and speeds up the training. So the input which is coming from input embedding mixed with the positional encoding, then it can go to the add and norms. So it helps to retain original information and speeds up training. Then it passed the input to the next one is the feed forward. After the attention mechanism, the data passes through a position wise feed forward neural network, which applies a transformation to each token. This network consists of two linear layers with a ReLU activation in between. So it helps in transformation of each token, Then again it passed the input to the add and normalization. So add and normalization again, the output from the feed forward network is again added to the input through a residual connection and normalized. Now this output from the add norm, it will connect to the another layer. So let me just draw the another layer. So this layer is NX and this is also NX. So NX, what is NX? This the attention, multi-head attention, feed forward, normalization steps are repeated multiple times. The NX represent that this block is repeated n times, commonly 6 or 12 layers. These repeated layers allow the model to learn more complex representations. That's why we call it as a NX. Now this is what we call it as a left side of neural network, and this is the right side of. Now in the right side of neural network starts with the output embedding. The decoder receives its input, which is typically the target sequence, like translated text in machine translation. These tokens are also converted into embeddings in the same way as the encoder. So this is output shift selected write, and if we write, typically target sequence. Now again it passes to the mask multi-head attention, but prior to this it again passed to the positional encoding. Similar to the encoder, here we have the encoder. Similar to the encoder, positional encoding is added to the output embedding also to provide positional information for the sequence being decoded. Positional encoding, understanding order of words. Now it passes to the mask multi-head attention. So this is mask multi-head attention. In the decoder, the first attention mechanism is slightly different. It's a mask multi-head attention where tokens are not allowed to attend to future tokens. This masking ensures that during training, the model does not look ahead at the correct future outputs, maintaining the autoregressive property of the decoder. Tokens not allowed to attend. Now, mask multi-head attention, it also pushes its output to the add and norms. Now, adds and norms in the similar way, it retains the original information and speeds up training. So, from here also, we can go directly to the add and norms, and from the add and norms it goes to the multi-head attention. The second multi-head attention layer in the decoder attends to the output of the encoder. So it receives the output of the encoder which gets the input to the multi-head attention. And add normalization also it provides the input here, and multi-head attention also associated with add and norms. So from add and norms also it can pass to the add and norms. So add and norms feed forward add and norms just like in encoder. So here we have the left side is the encoder and this is right side is the decoder. So as like the encoder, residual connections and normalizations are used after both attention mechanism and feed forward layers. This stabilizes training and retains information from earlier layers. So similar to the encoder, these attention, feed forward and normalization steps are repeated multiple times, due to which these are also called as NX. The deeper the model, the more abstract the learned representation becomes. Now comes to the final layer. So let me just draw the feed forward, and it is also associated with the add and norms, and this add and norms provide input to this feed forward, and it also associated to the add and norms. So this is what I previously explained about the add and norms, feed forward and add and norms. So the main task is for this is to stabilize training and retains information from earlier layer. Now next come to the linear transformation, which is the final layer, linear transformation. After passing through all the decoders, layers, the output is passed through a linear layer, which projects the vector into a higher dimensional space. This helps in converting the decoder's hidden state into a meaningful output, typically corresponding to a word or subword token. Then linear transformation, it passes the input to the softmax. So this is the softmax, and these both are the final layer. So what the softmax do? Softmax function is applied to the output, converting the raw scores from the linear layers into probabilities. Each probability corresponds to a possible token in the target vocabulary. The token with the highest probability is selected as the next word in the sequence, and then it provides the output to the output probability. So in the softmax, token with highest probability is selected as next word in sequence. So this is the complete transformer model. So if I summarize, here we have the encoder that processes the input sequence by applying multi-head attention, normalization and feed forward layers multiple times to learn deep representation. So this is the encoder part. Decoder takes the encoded information and generates the output sequence by attending to the encoder's output. So this is encoder, which is passing the input to the decoder using mask attention to prevent cheating, seeing future tokens during training. Then the attention mechanism allows both the encoder and decoder to focus on specific part of the sequence, making the model highly efficient at learning long range dependencies in text. So this is the overall architecture of transformers. Let's first discuss some principles behind the transformer architecture. So unlike earlier recurrent neural networks that sequentially process inputs, transformer process entire sequences in parallel. The architecture consists of two parts which we seen in this architecture in the diagram. Encoder is an LSTM that takes in a sequence of tokens and turns into a vector. The decoder is the another LSTM that converts the vector into a sequence of tokens. LLM largely represent a class of deep learning architecture called transformer networks. A transformer model is a neural network that learns context and meaning by tracking relationship in sequential data, like the words in the sentence. Now, understanding some important abbreviations. First one is FLAN. So, FLAN stands for fine-tuned language net, and in this T5, FLAN T5. T5 is text-to-text transformer. Text. The FLAN T5 model is an encoder-decoder LLM from Google, released in October 2021, which has been specifically fine-tuned using instruction tuning from Google, used for instruction training. Second one is BERT, stands for bidirectional encoder representation from transformers, is a machine learning framework for natural language processing. BERT is designed to help computers understand the meaning of ambiguous language in text by using surrounding text to establish context. The BERT framework was pre-trained using text from Wiki and can be fine-tuned with question and answer dataset. Pre-trained. Now the third one is Bloom. It stands for Big Science, Large, Open Science, Open Access, Multilingual Language Model. Bloom got its start in 2021 with development led by machine learning startup Hugging Face, which raised $100 million in May. Now, moving forward to the agenda, that is the deep neural network. So, this is deep neural network. So, deep neural network architecture which consists of multiple layers designed to learn complex patterns from data. Key components are the input layers. So, input layer. So, this is the first layer on the far left side where the raw input data is fed into the network. The number of neurons, nodes, what we call it as a nodes in the input layer, these are all the nodes, corresponds to the number of features of the data, features in the data. So these are the features data. For example, if you are working with image data, each pixel would be a feature and the number of neurons would be equal to the number of pixels in the image. So let's say that the image which consists of 1270 into 970 pixels. So these are the features that we provide input to the deep neural network. Now the next layer is the hidden layer. These are the intermediate layers between the input and the output layers. In the diagram there are three hidden layers, second and third, labeled as hidden layer 1, hidden layer 2, hidden layer 3. Each hidden layer consists of neurons that received weighted inputs from the previous layer. The input layer of hidden layer 1 and the previous hidden layer for the subsequent layer, these neurons then apply an activation function. They apply an activation function. Now the activation function, it consists of like ReLU, sigmoid, 10 hai. So we will learn more about this in our upcoming session. So here in this diagram, I am just explaining about that how the things are working, how the features that are coming from the input layer going into the hidden layer. And in the hidden layer, that is then applies an activation function to introduce non-linearity, allowing the network to learn more complex pattern. Now finally come to the output layer. This is the output layer. The last layer, which is on the extreme right, far right, which produce the final prediction or classification. The number of neurons in the output layer corresponds to the number of output classes or the dimension of the regression output. So these are the number of neurons that corresponds to the number of output class. For an example, if you are performing a binary classification task, the output layer might contain one neuron with a sigmoid activation to output a probability. For multi-class classification, the output layer may contain multiple neuron with a softmax activation. Now if you see here, there are the multiple connections. The lines connecting neurons between layers, these are the connections. It represents the weights. Each connection has a weight that is learned during training. The neurons in one layer pass their output of the neuron in the next layer. So it passes its neuron to the next layer. The neurons in one layer pass their output to the neuron in the next layer after applying weight and bias. Weights and bias. Initially, these weights are randomly assigned, and during training, they are updated through backpropagation to minimize the error. Now, if we talk about the activation function, every neuron in the hidden layer, this is the hidden layer, applies an activation function to its input before passing it to the next layer. The choice of activation function helps the model capture non-linear relationship in the data. So, common activation, as we discussed, like ReLU, that is also known as the rectified linear unit, linear. So these are typically used in hidden layers, allowing the network to handle non-linearity efficiently. For handling let me just write it again, non-linearity, for handling the non-linearity part. Now the sigmoid often use binary classification problem in the output layer, and the softmax use multi-class classification problem in the output layer. Now the training process, how the training process is. The deep neural network is trained using the backpropagation and the gradient descent. The forward pass, which we use in the training process, the input data is passed through the network layer by layer from left to right. Each layer processes the input using the weights and activation functions and passes the output to the next layer. So using the weight and bias and the activation, so they pass it to the next layer. This continues until the final output is produced at the output layer. We another term called as a loss calculation. Loss calculation. After the forward pass, the output is compared with the true labels using a loss function. Now the loss function, it consists of, for an example, like mean, squared, error for regression. These are the examples. Cross entropy for classification. The loss function quantifies how far the predicted output is from the actual label. Now the third one is the backpropagation. Backpropagation. The error loss is propagated back through the network, updating the weights of the neuron to reduce the error in the future iterations. This is done using gradient descent. Gradient descent, which is also we use it for the other optimization technique to adjust the weight in the direction that minimize the loss. Gradient descent to adjust weights to minimize the loss. Then weight update. The weight of the connections are updated at each layer, that is the hidden input layer, hidden layer 1, hidden layer 2, hidden layer 3. And this process is repeated for many iterations, that are the epochs. Iterations are called the epoch, until the model reaches satisfactory performance. So if I summarize it, the deep neural network shown in the diagram is a feed-forward neural network where data flows from the input layer to the output layer, passing through multiple hidden layers. These hidden layers allow the network to model complex relationships and patterns in the data, making deep neural networks particularly powerful for tasks like image recognition, natural language processing, and more. Okay, so that's complete the understanding for deep neural network. So let's see our agenda. So as per our agenda, we have completed the transformers, some abbreviations, deep neural network. Now we will understand about the training language model. Training language model. So here I use this diagram from Google by mentioning the training language model. So in the training language model, if we see, we can see the prompts dataset, initial language model, generated text, output are ranked, and the reward reference model. So what are these? So we'll look into detail. So this entire image outlines a process commonly used in training language model, specifically related to the reinforcement learning for human feedback. Reinforcement learning for human. Now let's try to understand and break down the image components. The first one is the prompts dataset. The process begins with a dataset of prompts which are sampled extensively to provide various inputs to the language model. These prompts might be question, task, questions, prompt can be question, task, instructions that the model will respond to. It passes the input to the initial language model. It is trained on these prompts to generate responses. This model is typically pre-trained on large corpora of text data and is capable of generating text based on prompts it receives. Generated text. Once the language model generates text in response to the sampled prompts, this generated text is passed on for evaluation. This generated text passed for. Now the human scoring, the generated responses are then evaluated by humans. We are the humans and we generally evaluate the input that received from the language model. Human scores assess the quality of the generated text based on criteria such as first, criteria for assessment, relevance, second, coherence, third, creativity. Based on this, human assess the criteria. The feedback provided by humans helps in guiding the training process by providing explicit scores or ranking for the outputs. Then the generated text, it trains on the sample rewards pair. The model is trained on pairs, sample prompts, human assigned rewards to improve its performance. Essentially, the human scores act as a reward signal that the model uses to adjust its future responses and better align with human preferences. Reward preference model is trained using the human scores to predict the reward that future output should receive. This reward model plays a critical role in fine-tuning the language model by providing a more automated way of scoring outputs, reducing the need for extensive human feedback. So outputs are ranked. The final output are ranked using methods such as relative ranking, example, ELO, ratings. So this is final output rank using this method. So these are methods. Relative rankings, well, example like yellow ratings to ensure the generated response meet the desired criteria. These rankings help in selecting the most appropriate or high quality outputs. So if I summarize this entire image, it illustrates how a language model is trained using a data set of prompts, human feedback and reward model to fine-tune the generated text and improve its quality based on preferences or rankings. This approach is key to aligning language models with human values and expectations. So this is the training language model. So now let's go back to the agenda. So as per the agenda, we have covered the training language model. Now the final one is the vectorization. I will go back. So here is the vectorization. So vectorization. So we'll try to understand the vectorization using this image. So this word vectorization in NLP specifically focus on how words are represented in a highly dimensional space through word embeddings. This technique is commonly used in GenAI model to capture semantic relationship between words. So here if you see in this x-axis and the y-axis, so there are some blue lines and some are the red lines. So the blue line which indicates the coordinates and the red line which indicates the semantic relationship. So there are the two x-axis and the y-axis, left and the right. So if we see, this is the left and this is the right one. So in the left side, if you see that the queen having the vector indexes 0.3 and 0.9. King here is having the vector indexes in 0.5, 0.7. Women is having 0.3, 0.4. Man is having the 0.5 and 0.2. Now this red arrow indicates in the left image, this red one. So if you see that the queen is associated with the women and the king is associated with the man. So this is the semantic analogy, where king is to man and queen is to women. So this analogy is reflected in the consistent direction magnitude of the red arrow, signifying the gender differences. Now the right side, if you see that we have again the blue which is defining the coordinates and the red which is defining the association, and it is showing the relationship. So here it is showing the gender and here it is showing the right side one is showing the relationship. So queen is having a relationship with the king and women is related with the man. So this is the kind of thing which we can associate in the GenAI. So in this we have some the key concept like word embeddings. These vector captures the semantic meaning of word. Words with similar meaning of relationship have similar vector, either in direction or magnitude. Another one is the analogy. This example demonstrates a common use case, solving word analogies like king is to man, queen is to women through vector arithmetic. The relationship between these pair word is reflected in the vector space. Another one is the semantic relationship. By learning these embeddings, model can understand and process word relationship in a meaningful way, enabling capabilities such as analogy solving, similar ranking, and more. So in a training setting for generative AI, such word vectorization help model understand and generate human-like language by preserving these relationships and meaning through vectors. This forms the basis of how model like GPT understand context and word relationship during text generation. So used in GPT word generations. So this is all about the vectorization. So as per the agenda, we learned about the transformers, some important abbreviations, understanding of the deep neural network, training language model, and the vectorization. So that is for today. So if you like this video, please like and subscribe the channel, and please share it with your friends and colleagues who would like to understand or like the Gen AI video. Thank you.